Okay, so here we go. So last time we were talking about vector line integrals. Remember, vector line integrals have a lot in common, have certain things in common with scalar line integrals. The big difference being what kinds of things are we computing, and specifically with vector line integrals, we're looking at line integrals of vector fields. Right? So the integrand is a vector, and furthermore, the differential is also a vector. There's something unavoidably orientation dependent about vector line integrals. It's the magnitude alone doesn't cut it, right? The size of the piece of curve does not cut it. You need to know the angle, the relationship, the directional relationship between the direction of the vector field and the direction that the piece of curve is oriented. Okay. All right. So for example, you can compute work, right? We did several calculations here of, how much work does it take to move along a certain curve while applying certain forces. Okay. So I want to take a slightly different point of view now, and I want to rewrite things to introduce the relationship to the unit tangent vector. Y'all may remember the unit tangent vector from a while ago. It's just the unit vector pointing in the direction that you're going. Okay. So here's the idea. Suppose you're moving along a piece of curve like this, and you've chopped it up into little pieces. Here's one of the little pieces of curve, and we've introduced this idea of the dx vector. Right? This is our position differential. And the whole idea of this position differential is it's something we can compute, right? It's v times dt, right? It's x prime dt. Its magnitude, remember, is ds. The first reason that we wrote down dx in the first place was because we were interested in computing that magnitude, that length, ds, which was the magnitude of dx. And then now, of course, the dx vector points in the direction of the velocity vector, which, of course, is also the direction of the unit vector in the direction of the velocity vector. I mean, this t vector, the unit vector pointing in the same direction the velocity vector points. There it is, same direction. Right? So dx points in the direction of t, a unit vector t, with magnitude ds. And as a result of that, I can immediately write down this result. Dx is Tds. That's just a different way of thinking about dx. I mean, our alternative, what we wrote down previously was that that dx was x prime dt. Right? So previously we sort of ran with this. Something nice about this point of view on on dx is that this is all in terms of the parameterization. This is part of a pullback, and once you've written down your vector line integral, you need to compute it. Very handy. But now we're going to go a different way with it, and we're going to reinterpret dx as tds. And what is this bias? Here's what you get. There's dx is tds. And then you'll notice I'm just going to kind of move parentheses around here a little bit to get this expression. Now, here's the thing. That looks like a scalar line integral. Look at that. It's got a ds on the end of it. So it is tempting to look at this and say, oh, okay, well then this was all an illusion. This idea that vector line integrals are different than scalar line integrals, we just weren't looking at it the right way. Look, because clearly integral over curve ds, scalar line integral. Well, the counterpoint there is don't fail to notice what's going on in the integrand. It remains that what is going on in the integrand involves a dot product. Dot products involve, what's the angle between the two directions. Specifically, a dot product with the unit tangent vector for the curve. This t here is not just a function of location. Right? The vector field is a function of location. You give me a point x, y, z, that tells me what f is. Right? But t depends not just on where you are, it depends on which direction is the curve going. Is the curve going that way? Is the curve going that way? Right? It is really more naturally associated as part of the differential. And it's really kind of awkward to have it seemingly inside of the domain here. So again, this direction dependence remains. It looks like a ds integral. It looks like an inert kind of scalar quantities only, densities and sizes and masses. But it's not. The direction still matters. Okay. All right. So anyway, that having been observed, I ask, is there anything that this does do for me? Rewriting the vector line integral as f dot tds. And yeah, there is something nice about that, and that is that this f dot t, keep in mind t is a unit vector. Recall from long ago, 3 weeks ago, that dot product of the unit vector means component. Okay? And so this gives us a different point of view on what vector line integrals compute. Previous to now, our main sort of physical geometric interpretation of this expression was, look, if F represents forces, then the line integral represents work. Right? We were thinking of this as a tool for computing work. And in fact, confession, this kind of an integral, it's really the only application I've shown you so far. Right? Normally we tried out a couple, 3 quickies, quick applications. I've shown you one application thus far of these vector line integrals work. But writing it like this allows us to kind of take a sort of another importantly different point of view. So here's let's draw a picture of this. So we're, on each little piece of curve, we're multiplying by the component of f in the curve's direction. So we're looking at these vector fields like this. We're looking at the component specifically. To what extent is that vector field pointing kind of along the curve? And now, the bad news is here, the sort of confession, what we're not going to do here is interpret from this a physical quantity that we already know about, right? Wouldn't it be nice if I could make an argument, trot, and oh my gosh, look at this, we just computed mass, or we just computed center of mass, or moment of inertia, something like that. It's not going to be a physical quantity that we're already familiar with. Nevertheless, it does give me the opportunity to reinterpret vector line integrals in terms of a different point of view on the vector field. Right? So if I were to interpret the vector field as representing a flow of fluids now, forget about forces. We're not going to think about forces and work, right? Our vector field represents a flow of fluids. Then kind of what we have here then is we're looking at to what extent is that fluid flowing along the curve. Sort of along the curve as opposed to in a different direction than the curve. That's what that component is. To what extent is the fluid flowing along the curve? And we're kind of adding that up along the entire curve, in a sense. So, why we would be interested in such a thing is, it might come up at some point in the future. Let me go ahead and, spoiler, it's going to come up plenty in engineering, right? Fluids courses need to talk about this all the time as it happens. Right now, all I can do is give you a kind of a hand-waving sort of, you can see how at least this somewhat naturally relates to thinking of fluids in a certain way. That we're looking at how much the fluid is flowing along the curve at each point, and we're adding that up along the entire curve. Okay. So what's the point of view? Okay. All right. Now, let me tell you what this is not. This point of view here. This is not something that I encourage you to think of as a computational alternative. This is not for computing. If you want to compute, every so often this is useful. But most of the time, when it comes time to plug and chug, this is not the way you want to do it. And here's why. So let's think it through. If you were to compute this, what is your ds? Well, ds is v dt, speed times dt, magnitude of velocity times dt. And then, well, wait a second. What is this t? This t is velocity divided by magnitude of velocity. So we've basically got what you might call a kind of a ridiculous situation of, we have in this line that we're looking at here, magnitude of velocity is in the denominator here, but it's in the numerator over here. Those just cancel. Or said differently, you could move this factor over next to this and recover what in fact is exactly v. Right, so the way that the calculation would proceed, if you try to do f dot t ds, you would in effect be doing what we already know how to do, f dot x prime dt. It's not buying you anything other than a short little jaunt around where you're computing square roots and multiplying and dividing by exactly the same thing. So it's kind of pointless. Okay, pause for questions about that. How are we doing? Okay. All right. Okay, so let's talk about these vector line integrals all together. This is my favorite sort of default notation for vector line integrals. What I like about this, a couple things. On the one hand, it's very compact, very crisp. Right. Secondly, this is really easy to relate directly to our primary application of this object. Namely, it's really easy to talk about why this computes work. Because you can see it right here in what's written, force dot displacement. It's bluntly connected to work accumulation. Last thing, and I think this is a big deal also. This dx here, that dx is telling you everything that you need to know for the purposes of this integral about the curve, a little piece of the curve. Let me draw that picture. If you have a piece of curve like this, right, your dx vector, vector like that, right? And this little piece of curve, what can I say about this piece of curve? Well, if I want to describe that piece of curve as relates to a work calculation such as we're doing here, I would need to say, well, what direction is that curve pointing? The dx vector is telling you the direction that it's pointing. Well, I'll also need to know how long, what's the length of this piece of curve? Okay, well, by its magnitude, the dx vector is telling you how long that piece of curve is. Everything you want to know about that piece of curve is encapsulated in that one vector. So this is a really nice this notation over here is a nice kind of breakdown between stuff that relates to the domain and over here stuff that it's not directly part of the domain and therefore should be thought of as the integrand. Okay, so it's very elegant notation in that sense. Okay. All right, so my personal favorite. But, of course, here and there, time comes up where, after relating to an application, you need to be able to compute. And this is, from the plug and chug point of view anyway, this is how you compute vector line integrals. Because everything here can be related to the parameterization. T, our parameter, is the differential. Right? So this is an integral in the pullback domain through the parameterization. The V, that is the derivative, the velocity of the parameterization. So this is your pullback integral. So this is a great way to think about vector line integrals as well. Now, it's not as immediately relatable to applications. Why is this equal to work? Well, you'd have to kind of say, well, okay, because see the velocity times the dt, that gives you your difference, that gives you your displacement along each little piece of curve, and then dot product with the force gives you work, right? So there's a little bit of a step there. So for application purposes, I like the previous. For computation, it's a little bit nicer. And then we just talked about this one. This is cosmetically, I suppose there's an appeal to this. I don't know. I guess it's sort of, I have a mixed mind on having this integral ds. It is familiar to have an integral of something ds, so that's kind of nice, I guess, right? But it's also a little deceptive. It's making it look like something that it really kind of isn't. Like, this is fundamentally a different kind of integral, so making it look like the old kind of integral, I'm not clear that that's a good thing. Okay. All right. Okay. And then here's the same thing said without the integrals, just from the point of view of differentials. These are the things that get dotted with f in each of the above integrals. They're just different points of view on what the dx vector is. Okay. Which, again, is kind of a vote for why that's the best notation, because the others are different ways of writing it. Right? So anyway, all right. Okay, so moving along, we're going to talk about a new thing now. We're going to talk about an idea called flux. We're going to build up to this idea of something called a vector surface integral. Real quick, remember we have already defined a kind of surface integral. We've already defined scalar surface integrals. If you have some surface and there's ants crawling all over it, you want to compute the total number of ants. If you're doing an accumulation on a surface, that's a surface integral, and we put the little prefix scalar surface integral on there. Right. So there is going to be, just like there was with line integrals, a completely, pretty different kind of integral also taking place on surfaces. This is going to be called a vector surface integral. So we're going to build up to that. Reminder, how did we do that when it came to line integrals? Right? Well, with line integrals, we looked at a physics application, work. Okay, so you all know what work is. Let's compute work. And you go out and you compute work, and well, we have a new kind of a Riemann sum that we have a natural justification for. I wish I could do that here, but we're not quite ready to do that just yet, because the physical application that we will start to work with, that will build up to this new kind of integral, is a physical quantity that y'all probably haven't seen before. Right, so the first thing I have to do is talk about the physical quantity. So it's a little bit of, it's kind of physicsy, but it's not that bad. So the idea, the physical quantity we're going to talk about is something called flux. Flux says if you have a fluid flowing, and remember we represent flowing of fluids with vector fields. And so here's a fluid flowing. And then if you have a piece of surface, like that, remember that the way that this vector field represents the flow of the fluid is that at any point, this tells you what the velocity of that fluid is. So we've got some, I don't know, maybe this is air blowing around, and this surface represents like a screen or something. This vector field is telling you what the velocity, feet per second, meters per second, whatever, that the air is moving at this point. So here's what flux is. Flux says, okay, yeah, that's nice to know feet per second at any point, but I would like to look at this entire surface and ask how much air per unit time is blowing through this surface. And again, not feet per second, but quantity, volume per second. So cubic feet per second of air blowing through that surface. Right? So it's a different thing. It's not, we're not going to be adding up the velocities exactly. It's not like we're averaging the velocities. I need to account for the velocity, but I also need to account for the size, the area. Okay. All right. So some things we need to worry about By the way, so this is our definition of flux. The rate of flow passing through the surface. Okay. So one thing we need to worry about is which direction are we going? Right. So do you mean that you want to know how much fluid is passing that way through the surface? Or, hey, I don't know, maybe you meant that you want to know the rate of flow of fluid that way through the surface. Right? Which direction is the positive direction? Clearly there is something opposite about, if there's wind blowing that way over there, but then there's wind blowing this way over here. These are clearly negatives of each other. Which one do you want to consider to be the positive direction through the surface? So this is a choice, right? There's no law that says up is positive. What if your surface was entirely vertical? I mean, is left by definition positive? Right? No, this is an arbitrary choice. It's part of the question. So the way we indicate what we call the positive direction through the surface is with what we call a unit normal vector. This is sometimes referred to as the orientation on the surface. Right? And it's just a way of indicating what we're defining to be the positive direction. Right? All right. Here's another thing. The direction that the fluid is flowing matters. Now, this is a silly thing, but I guess I don't have a piece of paper here, but let's suppose that instead of air and a screen, let's suppose we're talking about water flowing around out in the creek out there, and a net. I suppose we're catching fish in a net. Okay, so you arrange your net like this. Now let's say that the water is flowing this way, like that. Right, you're going to catch a certain amount of fish in your net because as that water flows through the net, you can just see the volume of water that's coming through that net, and whatever the fish population density is, then you can figure out how many fish. Okay. It's very important that you hold your net like this, not like that. Right? Does everybody see the point there? So the orientation, how that, it's not just a matter of area times, what's the velocity of the fluid. It matters that the net is oriented the right way. It's like this is the kind of the best, if you will, if the water's going like that. If you kind of do like this, you'll probably still catch some fish, but if you hold your net like this, okay, the fish are just going to go right on by and say, hey, that's weird, look at that thing, and just keep right on swimming. They don't get caught in it because they're not going through the net, they're going parallel to the net. You see what I'm talking about? Okay. So we need to figure out then, where's my picture? Did I? Okay. I guess I didn't draw this picture. Okay, oh well, no worries. We need to look at this vector field and identify two separate parts of it. On the one hand, there is the part of the vector field that is actually perpendicular, namely in the same direction as the normal vector. Right, and this is what I'm going to call F perp. And on the other hand, there is the part of the vector field that is parallel to the surface. I'm going to call that F parallel. Right? The vector field itself is the sum of these. Right? There's always a unique way to do this. I appeal to your geometric intuition. Given a vector field, there's a unique part of it that is perpendicular to the surface and a leftover part that is parallel to the surface. And we are interested only in the perpendicular part. Come on, color change. The perpendicular part. That's what we care about. That's what's going to catch us fish. To whatever extent the fluid is flowing parallel to our surface, it doesn't make any difference. It doesn't contribute to flow of fluid through the surface. Is everybody on board? Okay. So that's the big idea here. We're interested in that perpendicular part. We're not interested in the parallel part. We're going to basically just kind of throw that part away. This perpendicular part, the magnitude of that perpendicular part times the area. This is what we're going to define to be flux. And we use this Greek letter, capital Phi. Phi for flux, pretty natural to motivate. And appeal to your intuition. I mean, the units work out. The speed in the perpendicular direction is distance per unit time. Area is distance squared. Just from a unit's point of view, altogether we have distance cubed per unit time. That's volume per unit time. That's what we're interested in. Also, you may recall we did an application way back in at the very beginning of chapter 5. One of our first applications of integrals was to observe that if you're interested in water flowing through a pipe, how much volume of time is passing through the pipe, and we came up with, again, speed times area. Okay. So this is what we're interested in. Good news, this perpendicular component, we know how to compute components. Dot product with the unit vector, we're interested in the component that is perpendicular to the surface. N is the unit vector perpendicular to the surface. So F dot N is exactly what we're interested in there. Okay. All right. So here's how the integral comes up then. It's no big deal. I'm interested in total flux. I assert that flux is an accumulating quantity, a real simple appeal. Here's your net again, right? We're looking for total volume of water passing through the net. Well, the total volume of water that passes through this little piece of net plus the total volume of water that passes through that next little piece of net. I mean, grand total, every little molecule of water is going to pass through, well, one of those pieces of the net. And I want to know the total of all of them. So it's an accumulating quantity. Grand total flux is the sums of little pieces of flux that you get from each little piece of the surface. And as we just computed on each little piece, F dot N times area computes how much flux there is through that piece. Right, and therefore we end up with this new kind of expression. It's a Riemann sum. We're doing a limit of the sum. In fact, here we are multiplying by an area on the piece of surface. At a glance, this looks a lot like our old familiar scalar surface integral construction, because we've got something times area, and we're adding up over the entire surface. Again, well, it's not exactly the same though, because look what's on the inside here, right? This what you might want to call the integrand. It's not strictly a function of position. This integrand, I mean, the vector field over here is strictly a function of position, but this normal vector is describing the orientation on my piece of surface, right? So just knowing where you are is not enough. You need to know whether your piece of surface is oriented per that normal vector, or if it's oriented differently, it's going to have a different normal vector. So this is a significantly different thing. That being the case, I'm going to give it a different notation. Here it is. This is a new kind of integral. This is our vector surface integral. And again, the notation is just it's a rip-off per patterns that we've already established of what the Riemann sum is actually computing. How are we doing? Everybody on board? Okay. All righty. Okay. So, a little bit of terminology. Because this kind of integral is used to compute flux, we call it a flux integral sometimes. Vector surface integral also. Sometimes just surface integral. I like to throw in the vector prefix for clarification, but anyway, you'll also hear it called a flux integral. Okay. All right. So this thing, now I want to rewrite that a little bit. I've already made the complaint that if you look at this here, not everything that I have highlighted there is actually really to be thought of as integrand. I mean, really, if you get right down to it, this thing here is telling you about the domain. It's telling you the orientation on a little piece of the domain on which we're doing some calculation. So that kind of ought to be part of the differential, one could argue, as it is telling you about the relevant aspects of that piece of the domain. So moving the parentheses around like that, I'm going to call this the differential. And because this thing is now telling us everything that I need to know about a given piece of the domain, I'm going to give this thing a name. I'm going to call this the ds vector. All right, so let's take a look at it. What is this ds vector? This ds vector is a single vector telling you everything you need to know for this flux integral, everything you need to know about what's going on the piece of surface itself. The direction that this ds vector points, it's the direction of the orientation. Right? It points in the, it's telling you how that surface is oriented. What's the magnitude of the ds vector? The magnitude of the ds vector is the ds scalar. It's the size, it's the area of that little piece of the domain. So by way of its two geometric features, direction and magnitude, you're learning everything you need to know, orientation and size, of the piece of domain that you're actually looking at at that point in the summation. Okay, so again, I think that's very natural to give it a name and a notation. Okay. All right. So real quick analogy. I guess I'll zoom back in. This ds vector is actually doing something that's a lot like the dx vector. Y'all remember the dx vector. And I was praising the dx vector because it tells you everything you need to know about that piece of the domain. The dx vector, by its direction, tells you what direction the curve is going. By its magnitude, it tells you how long that piece of curve is. That's what the ds vector is doing, just with normal vectors instead of tangent vectors, and with areas instead of lengths. Okay. All right. Okay. Yeah. Also, so another thing. I mean, and this is just cosmetic. You could argue aesthetic, but there is again something awkward about this notation over here. This makes it look like we're talking about a scalar surface integral. What cosmetically appears to be the differential is a scalar, as was the differential for our actual scalar surface integrals. Now that's a little misleading. I mean, importantly, this is very different from a scalar surface integral. So having the notation make it look like something that it isn't, it's awkward, confusing. The ds vector solves this problem. This looks different. You can see in the differential how this is a different kind of an integral, and I think that's appropriate given that it is a different kind of an integral. Okay. Alrighty. Okay, so how do we compute these things? Yeah, okay. Well, a lot of this work is already kind of set up. Let me remind you, how did we compute scalar surface integrals? Well, we viewed the domain as an image of something that I like better, namely a rectangle, right? And they said differently, we parameterized the surface, and having parameterized it, we went to a fair amount of trouble, and we've computed a bunch of stuff doing scalar surface integrals. We talked about the image of E1 du being that vector. We talked about the image of E2 dv being that vector, and we computed correspondingly what this area is. That area, of course, we call ds scalar, etc. computed the stretching factor. Remember, the stretching factor was the magnitude of XU cross XV. I hope you all remember that formula. It's a good one. Okay. All right. So what are we computing here? By the way, here's another picture of our accumulated objects of interest. Here's that XU du, the XV dV. Right, here's the area, ds. Let's see here. We've previously discussed this unit normal vector. That's our orientation. Right, I just got through defining this differential vector, ds vector. That's our sort of all-encompassing, this tells me everything I want to know about that piece of area. Direction tells you orientation, magnitude tells you size in the area. And then there's this capital N vector that we talked about way back when we were talking about scalar surface integrals. That's just that's a shorthand. This capital N thing was XU. Whoops, put the little hat on the wrong. XU cross XV. All right, let's do it like that. So here are all the objects in play. Okay. All right. So here's a nice related calculation. Start off with the definition of the ds vector that we just talked about. The ds vector is little n ds scalar. Again, this is the most important way to think about the ds vector. This is the sort of all-encompassing. You can see the direction, you can see the magnitude. Both of these are naturally related to the piece of surface. But now, good news, we already know how to compute ds scalar. This is from a couple sections back. The ds scalar is the magnitude of capital N du dv. Said differently, magnitude of capital N is our stretching factor. Keep in mind this capital N, XU cross XV. Okay. Now again, I'm going to just play with parentheses a little bit. Move these parentheses around. Kind of group like that instead. And now what can I think of to say about this integral, this thing here? Little n times the magnitude of capital N. Well, here's the thing. Those two vectors point in the same direction. Right? Capital N is perpendicular to the surface because it's a cross product of two tangent vectors. Perpendicular to the surface, therefore pointing in that direction. Little n is perpendicular to the surface by definition. But these two vectors are parallel. So let's think about what we have down here then. We are now looking at a vector that points in the direction of little n and has magnitude equal to the magnitude of capital N. Let me say that a little bit differently. We're looking for a vector that points in the direction of capital N and has the same magnitude as capital N. It's got the same direction and same magnitude as capital N. It looks like a duck and quacks like a duck. It's a duck. Right? It is capital N because it's pointing in the same direction with the same magnitude. Everybody on board there? Okay. So we have our nice formula then for computing ds in terms of a parameterization. Everything that's over here on the right is in terms of the parameterization. Capital N is a cross product of partial derivatives of the parameterization. U and V are the pullback variables for the parameterization. So this is your pullback calculation right here. Everybody on board? It's kind of like this is the analog of, when we were talking about vector line integrals and we wrote dx is, and we had an easier calculation there, x prime dt. derivative of the parameterization. Hey, oh, by the way, capital N comes from derivatives of the parameterization. And then differentials of our pullback parameters in each case.
Okay. All right. So let's rewrite integrals then. Here's our flux integral, vector surface integral that allows us to compute flux. Previous to now, this was just a shorthand representing little n times ds scalar. But per the above calculation there, I can now write that as capital N du dv. Notice I have a pullback. This is now all in terms of the parameterization and plug and chug. Okay. All right. Let's do a calculate. Let's do an example. All right. So I'm going to look at here's a surface. Specifically the part of that surface that's directly above the unit disk in the xy plane. So z equals x squared plus y squared is a paraboloid, right? It's a bowl. We're looking at the part directly above the unit disk. So we're looking at this right here. Yeah.
There's that surface.
Now, a little detail to talk about. Notice that it says here further that our surface is oriented downward.
Okay, so we're about to ask a question about flux of a fluid through this surface. And you keep in mind, whenever you're talking about flux through a surface, you're imagining some fluid flowing through that surface, and well, you've got to decide which is the positive direction. I mean, if there's fluid flowing through like that, does that mean this is the positive direction? If the fluid just turns around, is this now the positive? I mean, you got to make a choice in advance. What direction is the positive direction? So this orientation, reminder, is just a way of indicating that choice. We're saying here, with oriented downward, that I want to talk about the downward normal vector, the downward through the surface. That's the direction I'm going to call the positive direction. And whenever fluid is flowing upward through the surface, I'm going to call that negative flux. How are we doing? Is everybody happy? All right.
Okay. So I've got a surface, an oriented surface, and then let's see here. Now I have a vector field, and let's compute the flux. Okay. All right, so here is our picture. By the way, here's our orientation vector. Downward through the surface. Oh, real quick talk about the orientation. You'll notice that this vector is not exactly pointing straight down, right? It's kind of off to the side a little bit. The language describing orientations is going to be unavoidably, I don't want to say sloppy, but let's say flexible. All right, and so here's our choices we have two different choices of orientation on this surface. One of them is what I'm going to draw like sort of this. This would be one choice for a reasonable option for what we mean by the positive direction through the surface. Here's our only other choice. Forgive my bad. Oh, a couple of these were really bad.
All these blue vectors are just the negatives of the green vectors that they're at the same point as. So these are the two reasonable orientations that I could make on the surface. The two notions of what is the right direction through the surface, and these are complicated. Right? If I wanted to perfectly and precisely describe this green orientation or that blue orientation, oh my gosh, I'd have to write down a complicated formula because there are different directions at different points on the surface, and my God, it'd be brutal. Right? So I guess you could do that, but the thing is, in practice, it's extremely convenient to try to use language to distinguish between these two different options without getting all technical. All right. So the idea then is, let's look at these two options. Let's look at the green versus the blue, and can we think of some characteristic that distinguishes between them? Right. And here's my choice here. I'm going to say that, look, all these green vectors are pointing somewhat downward. Right? None of the green vectors are pointing at all upward. Not even a little bit. Right? They're all pointing somewhat downward. The blue vectors are all pointing somewhat upward. So in this case, the word downward, again, while it's not a perfect description, it does unambiguously pick out green versus blue between our two choices of orientation. Everybody see what I'm talking about? So don't make them. It's a very common mistake for students to look at. Oh, he said the oriented downward. I guess that means capital N is 0, 0, -1. Well, it's not. That's not what we mean by oriented downward. We mean I'm trying to tell you with vague language how to distinguish between the two actual options. And 0, 0, 1 is not an option because, take a point up here, for example, 0, 0, 1 is not perpendicular to the surface. All right, so the best choice of language depends on the surface. Here's just while we're on this topic, let me point out, suppose that you're talking about a sphere. All right, and here's our two choices of orientation. All right, these vectors are all perpendicular to the surface. These vectors are all perpendicular to the surface. If you say upward or downward here, I don't know what you're talking about. Right? These green vectors, some of them are pointing up-ish, but some of them are pointing down-ish. Likewise, the blue vectors, some of them are pointing up-ish, some of them are pointing down-ish. The word upward just doesn't help me distinguish green from blue here. Everybody see what we're talking about? Downward, likewise, doesn't help. Leftward doesn't help. Rightward doesn't help. So, any thoughts here? I mean, how would you? What is it that? What is the? Don't sweat the details. But what is it that sufficiently accurately describes either one of these unambiguously distinct from the other? Any proposals? Yeah. It's exactly. So the green was pointing inward. All of these vectors are pointing inward, and all the blue vectors are pointing outward. Right? And even if they weren't pointing exactly, I mean, this is a sphere, so yeah, okay, fine, right? But even if it were like an ellipsoid, where the normal vectors weren't technically pointing exactly toward the center, yeah, okay, fine, but still, it does the job, right? I mean, it makes it clear which one of these we're talking about. So, if you are trying to describe an orientation, your job is to think about your two alternatives and use language that unambiguously distinguishes them from each other. If you are interpreting language that someone else has chosen, keep in mind that that's what they were doing, right? They were looking at the two different options and they were trying to come up with language that would, even though it's not technically precisely exactly, it helps you see which one of the two options they intended. All right.
Okay, so this is oriented downward. Now, here's another problem that we face, and I know I'm getting around to using this formula. Right, we want to do a computational example, but we're about to step on a landmine, and I want to point out the landmine, and then let's walk around it. So here's the landmine. I've got to come up here and draw another picture, and let me remind you about curves in computing vector line integrals. For example, we looked at this curve here, the upper semicircle, right, in the XY plane, and we parametrized it, going a certain direction. Why did we go a certain direction? Well, the question said, let's compute the amount of work that it takes to move from here to here. In fact, I think maybe the question, it might have even said moving counterclockwise around the thing, right? So an orientation was given to us. As well, of course, they better give you an orientation if you want to know how much work it takes to accomplish a task. Well, the opposite of the task. It's not the same amount of work, right? It's a lot easier to carry heavy boxes downstairs than it is to carry heavy boxes upstairs. When we parameterized this curve, we were paying attention to the direction we're supposed to go, and we went the right direction, right? We didn't even really think about it too much. We just made sure that when we parameterized the curve, we parameterized it in such a way that the parameterization went the same direction that we were supposed to go. Okay. We did have to think about it when all of a sudden the orientation changed. We were told, okay, let's parameterize one going clockwise, and then we had to think, okay, how do we do that? And we went to some trouble, different points of view on how to accomplish that, and we made a parameterization that goes clockwise. Okay, all right. Good news. When you're parameterizing a curve, you can just think about, well, which direction is this parameterization going? You can just think, well, what happens when t increases? As t increases, am I moving that way along the curve, or am I moving that way along the curve? The orientation is something that you can kind of see in the parameterization. Okay. It's not really with surfaces, right? If I write down a parameterization here, and by the way, here is the first step that we're going to do. The first step we're going to do with parameterizing that surface is write down the graph parameterization. Look at this formula here for the graph parameterization. Which direction does that parameterization go? Does this parameterization, is it oriented the right way, or is it oriented a different way? It's really hard to tell. It does not leap off the page. You can't just think about, well, follow T and just go the direction T goes, right? No, it's not like that. Okay. So we face a new problem. Back when we were dealing with curves, the way we made sure that we parameterized the correct direction is we just, parameterize the correct direction. Right? Now, we're flying blind. When we write down a parameterization of this surface, it's not clear that we're going to parameterize it the way that we're supposed to. We're supposed to parameterize this thing downward, but when I write down a parameterization, I haven't got the slightest idea which way that parameterization is going to go. Okay, so here's the landmine. The landmine is you might inadvertently parameterize backwards. And if you do, you're going to find yourself computing flux the wrong way. Everybody see the problem? Okay. Here's the good news. The good news is that the difference between parameterizing the right way versus parameterizing the wrong way, these two vectors are exact negatives of each other, right? So if you parameterize it the wrong way, you're going to get the negative of the correct answer. So we can resolve this whole problem by finding a way to identify whether we parameterized correctly or not, and then, if necessary, stick a minus sign on our answer and declare victory. So that's what we're going to do. So it turns out to be not as hard as you might think. Here we go. There's our parameterization. Our parameterization allows us to compute n. Remember, capital N is XU cross XV. Right? A couple of details, partial derivatives, compute the cross product, blah, blah, blah. And here's the n that we just computed. And from this, we can now take a pause and realize whether we have inadvertently parameterized this the right way or the wrong way. Now let me remind you, we were asked to parameterize downward. So what I need for this to have parameterized correctly, I need for my normal vector to be pointing, air quotes, downward. Okay, what I mean by that is somewhat downward as opposed to upward. A little bit more precisely, I need for this normal vector to have a third component that's negative. Right? So if my normal vector that I just wrote down, if its third component is negative, then I parameterized the correct way. But if the third component is positive, then I inadvertently parameterized the wrong way. And it's a real easy check. I just come down here and see, and drum roll, our third component is positive, and therefore upward, and we parameterized the wrong way. Yeah? Everybody good? Okay, so you just have to keep this in mind, right? Whenever you're doing vector surface integrals from a parameterization, just realize that there is this landmine because we can't tell what direction we're orienting as we're parameterizing. When we write down a parameterization, we're writing down an arbitrary, unintentional choice, and it's a coin flip as to whether we're going to be right or wrong. So you just have to check, and give me 2 seconds. Having realized here that I've parameterized the wrong way, let me show you what I want you to write on exams or homework exercises. I want you to say here, wrong orientation, frowny face, for example. So and point to the negative sign that you're inserting in there to account for the fact that you inadvertently parameterized exactly backwards and therefore got exactly the negative of what you should otherwise have. And by sticking in an extra negative, you're now all set. Yes?
Does that work for, I guess, inward and outward as well?
So there'd be a different cue. Here, the third component was the arbiter, right? Because our two choices were upward versus downward. Yeah, if it's inward versus outward, you're going to make different choices. So one thing you might do on a sphere, for example, write down your formula for your normal vector, and then pick a point, like plug in the North Pole. And for that point, North Pole, you got to compute out and see exactly what that vector is. And at the North Pole, you better get either straight up or straight down, and then that'll decide for you. Yeah. Does that make sense? Yep. So you're right. It's a different. The third component does not always make the distinction, but somehow or another you have to make the distinction. Was that yeah?
If it's by the negative in front, is it cool to just flip the vector right there?
So, and I hear you. I'm going to say no, and the reason why is because capital N is something that is dependent on the parameterization. So you're not actually changing your parameterization. We're going to continue with this parameterization. So we're not changing this, right? So because x is still the same, you can't just say, oh, I'm going to redefine xu to be negative xu. That doesn't make any sense, right? So everything that you derive from the parameterization, you really have to keep. So xu is what it is, xv is what it is, and n is what it is. You can, however, say that the question that I was asked is the negative of the question that I guess inadvertently I'm technically answering. Yeah, right. But yeah, don't just stick a minus sign on the end vector. Yeah. Okay, let's finish this super quick and then we'll take our break. But it's all over with the shouting at this point. The vector field, of course, you just pull back. We rewrite the vector field in terms of the parameterization. Remember, the parameterization tells you what x, y, and z are. X is u, y is v, z is u squared plus v squared. Plugging into the formula for f that's on the previous page, that's what f of the parameterization is. ds is n du dv, and we just computed in up there. Right, this n is there.
So note, all I'm doing is, this is just plain old plug in, right? Plug and chug, as it were. And then you can, once you've got everything in terms of U's and V's, then you can actually execute the dot product. You get a double integral over the pullback domain, which is the unit disk here. And by the way, I think polar coordinates, it's a great way to work out this integral. This is just a double integral. You can compute this double integral by any means you want. And polar coordinates in this case turns it into this. And that's perfectly computable. Okay, how we doing? Is everybody happy? Okay, let's take a 10-minute break. See y'all 11:20.